This is the last of our four-part webinar series, and if you remember at the beginning of the month we talked about what our objectives were with this webinar series, and primarily they were to do two things. One was to discuss the load path continuity issues and the important things about load path continuity for high wind design, and we wanted to take that load path from the top of the building to and through the foundation. And the second objective was to use the wood frame construction manual and the new version of it, the 2012 version of it, to discuss where the loads come from in the manual, how they're applied to the building, and what other design information was available to practitioners in the wood frame construction manual. So hopefully you have found this helpful in meeting at least our two objectives of putting the webinars on. Buddy, I think, mentioned that if you do have some questions, please type them in the question box and we will take them at the end of the webinar. And if for some reason we don't get to all of them, the American Wood Council will provide a response to everybody so everybody knows what the questions were and what the answers are. So with that, let's get rolling. This is a slide you've seen now for the fourth time, at least in this series. You are certainly welcome to use the materials that are in this webinar, but please get permission from the American Wood Council before you do. We would like to get the information out, obviously, into lots of hands, and so I guess from my standpoint this is encouraged, but this material is copyrighted, so please treat it with that kind of respect. So the learning objectives that we have for participants today are to understand the concepts of load path for wind pressure applied to buildings, and this really means into and how it's distributed into foundations. We'd like for you to be able to describe at least a couple of foundation systems that are best suited for wind and flood loads, and to understand something about likely foundation failures that are attributable to wind only. Now, I haven't mentioned it in the introduction yet, but we will shortly. We can't really talk about foundations, at least in coastal areas, without talking something about flood and including flood as part of the design parameter. We're going to do that today too. It's going to be at a really high level. We're not going to really get into flood loads or anything because that's several webinars worth of material in and of itself. But we do have to talk about flooding when we're talking about high winds, if we're talking about buildings obviously built near the coast or along coastal waterways. So that will be part of our discussion this afternoon. The series, just as a reminder, is coming from the 2012 Wood Frame Construction Manual. The loads and the information developed is all coming from that document. We have tried in this series to follow the prescriptive provisions as much as we can, and they are in Chapter 3 of the manual. And you see the sections that deal with prescriptive provisions for connections, floors, walls, and roofs. There are numerous construction details and load tables in the manual. You know that from the previous webinars and probably from your own use. And the manual has a chapter focused on engineering design. So when you're outside the parameters of the prescriptive limitations of Chapter 3, then you can use the information and the guidance and the formulas that are in Chapter 2. So today what we want to do is look at pile foundations. We're going to use the loads to the piles that we developed from last week's webinar. We're going to look a little bit at pile design and lateral stiffness of foundation systems. And we're going to look at crawl space foundations. Again, the loads are going to come from last week's webinar and from the wood frame construction manual, because here we can get some loads from the manual. There are some important flood-related crawl space design issues that we'll mention, with the focus really being on flood damage prevention. Now, the other thing I think I mentioned in one of the previous webinars, but just as a reminder, Most of the prescriptive load information that we have available to us as practitioners pretty much stops at the floor to foundation interface, and it does in the wood frame construction manual as well. So when we take these loads into the foundations, I'm going to sort of be going off the reservation from a prescriptive load standpoint, but trying to provide some background about how we think these loads are applied to foundations, why we do it or suggest the designs the way we do. And so I guess I'm kind of expecting there might be a bunch of questions about that, and I'll do my best to try to answer those. So just as a reminder, we have the vertical loads on a foundation system that have to be carried to the soil through the foundation, and one certainly is dead load, and one is live load, and the live load can be obviously roof live load or live load on a floor. And then we've got wind load, and the wind load in this particular case is all showing vertical. Remember, this load is normal to the surface that it acts on. So basically for vertical loads, we have three primary loads to consider in terms of taking loads to the foundation: dead loads, live loads, and the consideration of wind loads. In terms of lateral loads, we have primarily wind, and in this case obviously showing coming from the left-hand side of the slide, and we have flood. So these winds and flood will typically operate or influence two entirely different parts of the building. So while the wind load can occur below where the floor system is, it typically cannot occur in the same place that flood loads occur. So when we have a hurricane or a tropical cyclone system of some sort, and we have wind blowing at the same time we have flooding, we do have a wind-water interface, and typically there's very little overlap of that interface except what might occur where waves strike buildings, etc. So where we have wind loads and flood loads, those are going to occur sort of not independently, but they're going to occur on different parts of the building. And then where we have flood, we typically have scour. So I hope you saw the little scour thing pop up at the bottom. Scour to us in this presentation and talking about foundation design is important because scour is the washing away of supporting soil around the foundation element. If it's a pile or a column, typically that scour occurs conically and will reduce the amount of support, lateral support, that soil provides around that foundation element. If it's the corner of a building, it can take out several feet of supporting soil underneath a crawl space foundation, for instance. So scour is important because it reduces the amount of supporting soil we have, either for piles or columns or for spread footings or continuous footings like we might have under a crawl space. There is a limitation in the first section of the wood frame construction manual. This is just repeated. This is just a repeat of that limitation, and you can see basically what it says, that the provisions in the document are limited to the attachment of the building to the foundation. So the loads that are in the wood frame construction manual get us down to that interface, and that's where they stop. And then engineering beyond that is up to us and either the governing building code or other engineering designs and standards that we might need to use for the design of the building foundation. So let's speak about flood first. This is a list of flood design references that I know are out in the practice and that people frequently use. So just very briefly, the first two are American Society of Civil Engineering documents. ASCE 7 has a chapter on flood loads. It's chapter 5. ASCE 24 is a different standard and focuses on flood-resistant design and construction. It does not have load information in it, but it does have information in it related to issues important in design. So it does talk about, has sections on deep foundations and pile designs, talks a fair amount about scour and erosion and how those can be determined, etc. And talks about not only foundations, but lots of other issues related to flooding. The Corps of Engineers, which are the next two documents, have design manuals. The Shore Protection Manual is huge. It's on the internet. It's available for free, but there's a tremendous amount of information available there. FEMA 55, you've heard referenced before. This is FEMA's Coastal Construction Manual, which is also available for free. And FEMA's got technical bulletins on specific issues, and we'll talk about one of those today that are also free on FEMA's website. There are flood mapping standards that FEMA has. We're not going to talk about flood maps at all today, but flood maps help define what we think the flood risk is. And then there's a design document that was written after Katrina, called Building Strong Foundations, focused specifically on prescriptive foundation designs for very high wind and flooding arenas. And there's designs in there, actually, CAD drawings and whatnot, with a lot of information about what was assumed to develop those prescriptive foundations, so you might find that helpful. The loads that are primarily cause us a problem with flooding are standing water, hydrostatic loads, moving water or hydrodynamic loads, breaking wave loads on piles or foundations, and then the loads generated by floodborne debris. The information that we need to design a foundation includes these bullets, and you might think of one or two other pieces of information that would be helpful. Certainly the first is how high do we think the flooding is going to be? Is the flooding in what FEMA calls a velocity zone where we get waves, or is the flooding in a more of a riverine area where we would expect water to rise and then fall, but not come with very many waves? So it just depends on the kind of flooding that we get as to how we're going to proceed with the design. But the depth of flooding is an extremely important starting point. And in most cases, and in most of the 20-some thousand communities that belong to the National Flood Insurance Program, most local governments adopt a freeboard requirement, which is a requirement of additional height or elevation above the regulatory flood elevation. Again, this is a topic we could spend a lot of time on, but the height of flooding doesn't just come from the map, or excuse me, the design information doesn't just come from a flood map, which is where we might get the height or the elevation, but can also include whatever the local community adds on top of that for additional protection. If the velocity is coming, if the water is coming with some velocity, excuse me, then we need to know what the expected velocity is. And that frequently occurs, obviously, in a coastal storm, will very often occur in a riverine flood. If you've been watching the news over the last couple of weeks, there was a lot of velocity of water in Colorado and the flooding that has happened there, so we can get velocity in lots of different watersheds. If the water is carrying debris and is likely to strike a building, then we need to know what that anticipated debris is. And when the water moves past an object, again a building, a pile, or a column, it's going to create scour at that particular element, and over the course of a wide beach or a wide floodplain can cause erosion in addition to that. And we need to protect the building, if you will, with foundation designs by possibly anticipating erosion from multiple storms. So this is a several-sided coin that needs a fair amount of investigation and judgment by the designer. There are frequently bracing requirements for lateral loads, certainly from wind, sometimes from flood, sometimes from earthquake, sometimes by the owner, because the lateral load, the bracing required for a lateral load might be more of a serviceability issue in terms of motion perception than it is a problem of a P delta effect or the building being pushed over too far. But however it comes about, there are bracing requirements most often. There can be foundation constraints on what you can use, so some of this could be driven by the community. Could be a town or a city, or it could be a neighborhood or a community association, or it could be the environment in which the material is being used. In some places it makes more sense to not use wood because of wood borers or bad termites or something, and maybe some other material is really more appropriate. And then, of course, in order to design a foundation, we need to know what the loads are and how and where to apply them. The foundation method that I've used most often and that I see lots of other practitioners use is a pretty cryptic method. Let me just go through it kind of quickly. We need to pick a foundation material that's consistent with what we think the loads are and what the hazards are that we've identified. We obviously have to select a height based on the evaluation of all the possible flood conditions. Now, that height might be driven to some extent by a height restriction in the community, or it might be driven by an owner wanting to make sure that their building is well protected from a flood. Could be driven by lots of things, not necessarily just the limitations or the requirements of a flood map or a community ordinance. We calculate the flood forces from our various flood elements, create a pile layout so the piles aren't too close, yet they're far enough away to be, where we have a cost-efficient design. And I don't know what too close or too far away is. Most pile-supported buildings in coastal areas are on the range of 8 to 12 or 14 feet on center, depending on the loads, obviously, and the size of the piles and other things. Then we determine what the loads are based on the pile spacing we have assumed, and we determine what our pile of embedment is based on those loads and those pile types and spacing, and then we iterate on a solution. And then we iterate until we get piles that are not overstressed. So we're looking for a situation, obviously a design condition, where we don't overstress the piles. Our flood design information, at least that's been developed by FEMA over the years and that I have used most frequently, really comes from what has not worked. So our failure experience has really driven what our designs today and our design guidance today looks like. So we have seen shallow foundation failures for sure. Some of those failures have been for really pretty big buildings, multi-story condo or apartment buildings built right on the water at a time when the flood maps for that area allowed shallow foundations, and then a storm comes along, knocks the building down. And it knocks the building down by eroding underneath the foundation and causing a foundation and a building collapse. So that is primarily how shallow foundation failures occur, is using the wrong foundation system for the hazard that is actually in play. See lots of cases where pile embedment is not sufficient. So people typically around the Gulf and Atlantic coasts in many places use pile design parameters, if you will, that have been used for years and years. And that most likely means, pile driving equipment that's been used in a business for a long time, driving piles to some arbitrary embedment depth because whoever's doing it has not apparently seen failures. Well, when a storm comes along, let's use Hurricane Sandy as an example. Storm comes along that hits a place that hasn't been hit in a long, long time, then designs and construction details that had worked for years all of a sudden don't work because that area hadn't seen a storm like that. So we're trying to add a little more science to pile embedment and pile design, that hasn't been done for a long time. There are enclosures below the flood elevation that can add load to the foundation, and those enclosures have to be well thought about. And in fact, many enclosures are not permitted by the National Flood Insurance Program for that very reason. So designers have to know what they can and cannot do below the flood elevation. We certainly get storm surge and waves that cause a lot of damage, and as soon as the waves start to crash into the wall of the building, most buildings will fail. If we can get the building high enough to have storm surge and waves just go under the foundation, under the foundation, under the floor system, then the building will generally make out fine. But once those waves get high enough to actually slam into the wall, and it's only got to be 6 inches to a foot, then there can be a lot of damage. Erosion and scour occurs frequently. We have to design the loss of soil into the design for a new foundation. And then I've already mentioned the issue with floodborne debris, and then the importance about at least thinking about and planning for that debris. The designs that I have done, I have typically tried to design to prevent failures. So in most cases, I try to get loads to the LRFD level, the ultimate stress level, because I frankly, at least for what I've seen happen in the field, I care a lot less about just overstressing a pile, having exterior fibers stretched in a pile. I care that this doesn't happen. So what we're trying to avoid is a pile snapping off like you see here. Now there are some embedment issues here as well. You can see the piles that are leaning here are leaning because they're not very deep in the soil at this point. So they have been allowed to rotate. The load obviously is coming from the water. You see over here on the left, so the loads are coming from left to right. And they have obviously stripped the building off of the foundation, and when they stripped it, they allowed, they pushed these piles over. So the loads that we apply to foundation designs look like this graphic. These are the places that we apply the loads. This graphic, again, is coming from FEMA's Coastal Construction Manual. What you don't see in the graphic is a vertical load downward. I guess maybe we thought it was too obvious, but so you definitely have to apply whatever downward load there is in dead and live load, and then apply a wind load both vertically and horizontally. The horizontal wind load is taken into the top of the pile, and it's taken in obviously through the floor systems and in shear walls. The water loads are taken someplace in the water column. The breaking wave loads and the debris impact loads are taken at the top of the still water elevation, and you see them shown at the top of the dark blue area designated by a flood. And then the hydrodynamic load, the moving water load, is taken halfway in the water column. Buoyancy forces need to be considered. They don't come into play much in a pile foundation, but they could come into play certainly if you were trying to flood-proof a building, keep water out, or into bigger structures. So it's shown here so we don't forget it. When we design a pile, we take that lateral load at the top that you see here in this graphic, and we basically treat the pile as the cantilever beam, a single cantilever beam. And so it deflects like you see the deflected shape, and the point of maximum moment, the point of fixity of the pile, is some distance below the surface. And so part of the design scenario clearly needs to be, so where is that point of maximum moment, where is that point of fixity, because obviously that's going to drive pretty much what the unbraced length of this pile can be, and therefore how big the pile is, or how closely they're spaced, or the material that they're made out of, or the bracing that's required, or all of the above. So the point of fixity, and I'll show you a formula for this in a minute, is driven primarily by the stiffness of the pile material and the subgrade modulus of the soil. What's important about this graphic is that the point of fixity in the design should be wherever you think the point of fixity is at some point in the future. If you just did this today at a site location and you shot the elevation where I'm running the cursor right now, and you assumed a little bit of localized scour if a storm comes along, then you'd have the point of fixity at whatever is defined by those limits. But if you consider long-term erosion of multiple storms, and so you're expecting to lose more on this surface than what you see today, and then you have localized scour, and then you find the point of fixity, it could be down here somewhere, which means obviously if it is, you also have a much better chance of having a pile survive multiple storms, but it also means a longer pile and maybe bracing, etc. The effective length of the pile is found by this formula. So you see, as I mentioned, the distance d, that point of fixity, is driven by EI, the stiffness of the pile. So you need to know, what the modulus of elasticity is in the moment of inertia, and it's driven by the subgrade modulus. This table of subgrade moduli, is taken from FEMA's Coastal Construction Manual. You can see the soil types are pretty broad in terms of categories or classifications, and you can see there's a pretty wide range in subgrade reaction in pounds per cubic inch with that wide range. So in order to get better at this and define it better, obviously you would need some maybe more geotechnical information about the site, and you could do a better job of picking a subgrade modulus, which would certainly improve the quality of the design. All right, so now that's kind of how we start on the foundations and the elements of them. So now it's time to move into figuring out what we do with loads. So without spending a lot of time on the quantity of the loads, I just want to go back to this graphic we had from the last webinar and look at the loads at the connector, so at the top of the pile, if you will, between the floor system and the pile. And we have an uplift load on that at that point of 960 pounds, a lateral load of 1290, and a shear load of 1090. Now these aren't really all that big loads. So for an example problem for this pile design, this won't net us a very robust foundation necessarily. But again, this is determined mostly by the wind loads in this case, because all these that you see here are wind loads taken in to the top of the pile and the pile spacing. I want to go back to one point made last week to just clarify something. So you see the connector that is right here, this hold-down connector that's at the edge, in this particular case, of a window. So this hold-down connector was illustrating a hold-down required in this segmented shear wall. And I mentioned last week that these connectors are used and need to resist both tension and compression. The correction there is they definitely resist tension. They are intended and designed to resist tension, and that's why they are connected in this way. When they act in the opposite direction, and this becomes a compression load here, the compression is taken into the lumber, into the sill plate, into the floor system, into the beam. So the lumber in these cases is resisting the compression, not the connector. Now, that goes to another point, however. Some of these connectors could, in fact, in a pile-supported foundation, be someplace in the middle of the span. And whether the connector is in tension or compression, you do have to design then the beams or the floor system to be able to resist additional moments caused by the tension and or compression in these hold-down connectors. This is a floor wall assembly for piles that comes from the Wood Frame Construction Manual. Put it in to illustrate that, in fact, the American Wood Council has certainly considered this an important issue and connection, and you see how they have summarized, if you will, how some connections can be made. And just very briefly, on the graphic, the cross-section on the right, you see the floor system coming in to sit on a girder. The girder, in this case, is notched into the top of the pile, and there are requirements really that the pile cannot be notched more than 50%. So this girder frequently and should be really fully supported by the pile connection, as you see it here. And then you see a note that says steel strap, and you see a bunch of nails that connect the load path from the wall stud all the way down to the girder. So that's one connection method to make the load path continuous from the wall down to the pile. So let's look at an example pile layout. This is our 20 by 40 foot building. I'm the graphic artist here, so hopefully I got all these piles lined up and they're all the same diameter. And they are intended to be spaced 10 feet on center. So we have a building that's 40 feet long and 20 feet wide. And in our case, we had wind, or I've made the wind blow from the bottom of the slide. So the red arrow indicates where we have wind. The load, I assume, the load is distributed at the floor level into all the piles, as opposed to just along shear walls or whatever. By the time this wind load gets into the bottom floor system, I think we need to use all the piles in order to help resist that lateral load. And so that's what basically I assume when I do a foundation design. We also, in this particular building, though, have shear walls, and those shear walls are at the ends of the 40-foot long segment. And so where we have those shear walls, we also need to make sure that that shear is taken out in the beam system and across those three piles. Additionally, this is the load that is taken into the floor system. So the load at the bottom, at the interface between the bottom of the wall and the foundation, is 129 pounds a foot, and the shear on both walls is 436 pounds a foot. Let me just put these other elements up here. Now, a question came up in pulling the presentation together. What about, so how would we distribute this? Well, you see the blue lines were really intended to represent a tributary area of 10 feet wide, and so each pile would take a lateral load of 1,290 pounds, and that's what was on, I don't know, several slides ago where I showed the loads from last week's webinar. But in this particular case, and certainly with this design, you still got 5 feet of tributary area here at the end, and so in addition to having a shear wall that's got 436 pounds a foot in it, this last row of piles would have to carry or take this 5-foot wide tributary area times 129 pounds a linear foot. Now, that's a pretty low load, and in the size of the connections and in the forces that's generated, that's kind of in the noise, if you will, because you're just not talking that many pounds distributed to 3 piles. So in our particular example problem, just to get down to the numbers, we had a building that was that weighed 40 pounds a square foot. You see the size. Remember, the wind speed was 140 in an exposure B condition. So when we have a lateral load at the foundation level, then that lateral load is 430 pounds at each pile. The maximum shear wind load at the foundation level, since we've got piles spaced at 10 feet on center, is 4,300 pounds, 4,360. And the uplift from wind is 970. So the way this typically works is just like in wind, at least I assume everybody does this with wind design. You look for the worst conditions and then typically design everything for the worst conditions unless those conditions are so bad or it's focused on just one part of the building that allows you to increase resistances in just one part. We're going to design all the piles basically for the same load. We're going to have all the piles be the same size. We're going to drive them to all the same depth. We are going to make the connection between the piles and the beams or girders all the same. So whatever the number of bolts are and whatever the diameter, they're going to be all the same. If we did anything different than that, we would have a mistake on our hands. I'm sure everybody would be familiar with how that would happen. The only thing that could be different might be, at least in this case, that for shear walls, we're likely to brace those shear walls potentially and maybe not need braces anywhere else, or maybe only need braces in the corners perpendicular to those short walls, and then we wouldn't need braces anywhere else. That would be one of those places where we could make a change, and contractors would find that perfectly normal and would know how to deal with it. So now let's look at how long the pile has to be. Most of these, as you can tell, are assumptions because we're just making up something here so we have some numbers to work with. If we assume that our base flood elevation is 10 feet high, 10-foot elevation, and we have a requirement in the community to add 1 foot of freeboard, then our elevation is 11 feet. Our lateral load from wind is at least 1 more foot up the pile, and so here I've said it's 12 feet. If you have a floor system and a girder, or a girder somehow that's stacked on top of each other, this could easily be 2 feet. If you have an existing ground elevation of 4, then your height from where the lateral load is applied to the ground is 8 feet. And to that 8 feet, we have to add this depth of fixity. If we assume a pile size, and here a 12-inch round wood has been assumed, and we assume a soil type and subgrade moduluses of 500 to 1,000 pounds a cubic inch have been assumed, then our depth of fixity is 3 feet when we have a subgrade modulus of 500 and 2.6 feet when it's 1,000. So as you might imagine, the stiffer the soil and the stiffer the pile material, the smaller D is. And just for the heck of it, I put together this little chart about what material comparisons provide in terms of variations in the depth of fixity. And you can see there's really not that much difference from a 16-inch square wood pile with weaker soil to a 12-inch round FRP pile with stronger soil, stiffer soil. That's a little bit of difference, 1.6 feet maximum, but anyway, just to show you what the variations are in depth of fixity based on stiffness and soil modulus of subgrade modulus. So in our example, if we had H of 8 feet and we assumed 12-inch round pile, our field data would suggest we get 2 feet of scour. If we assumed some long-term erosion of 2 feet, and that's why the question marks are there, it would be a judgment that we would apply. And we use a 12-inch round pile with a sand that I assumed, and so our depth of fixity is 3 feet. We have a 15-foot long length of pile when that pile is 12 inches in diameter and it's wood. We still haven't driven it yet, so the length of the pile from the load to D is 15 feet. We do need to care about axial and bending stresses, combined stresses, so I use this formula to determine what the combined axial and bending stresses are, and frequently I will set this equation equal to 1 and work my way backwards to what L, the maximum L, can be to not have excessive stresses. So, and I would do that by figuring that the bending stress, F sub B, is driven off of a cantilever beam. So the moment is, L times whatever the force is. So anyway, that's a frequent way to handle this without getting too wrapped around the axle about what the length needs to be. We certainly have some overstress solutions for piles if in fact we go through all this calculation and we still have a pile that doesn't work, or we don't want to change the spacing or the diameter or whatever, then we can brace it, and there are several ways to brace it, and I've got some pictures here shortly. Or we can change the pile spacing, or we can change the material, or we can stiffen the pile at a critical section, although I've actually never heard that done, although I've heard some conversation in the field about looking for ways to do it. I've never seen it done. All right, now let's go to crawl space foundations briefly. We have the same loads now that we had before on a pile system. Here you see the loads in pounds per linear foot. We're going to resist these loads by anchoring a sill plate to, in this case, a masonry foundation. And we're going to do that with bolts. And so typically, what does that mean for us? It means that the bolts have to be spaced a certain distance on center. The bolts have to be such diameter with a washer on them so that the head of the washer doesn't get pulled off, or that the sill plate doesn't pull over the head of the washer, or that the anchor doesn't pull out of the masonry. All those things are possible failure modes. So if we look at spacing for a minute, we know that the governing IRC requirements typically, currently have a maximum spacing of 6 feet on center. Our embedment depth for the anchor bolt ought to be governed by uplift loads and thickness of the crawl space walls, meaning that if we had a, 5/8 inch diameter bolt and our loads were really high and we tried to use a 6-inch masonry wall or something, we almost don't have enough space to get that bolt in a 6-inch wall and have enough cover for the bolt to actually be able to be used for much embedment. So you just have to, I'm sure everybody on the call is used to trying to marry up all of those requirements and get a wall design that will work. The walls have to be designed for lateral and shear loads at that sill plate foundation interface, of course, and then the loads have to be carried all the way into the foundation. So this load path continuity has got to go from sill plate to bolt to masonry wall to footing. If we look at a sample foundation design and assume an 8-inch masonry wall 4 feet high from the footing to the sill plate, if we had number 4 bars at 4 feet on center, we'd have plenty of capacity for wind resistance. But that's something that typically needs to be engineered and is, I don't know really of a prescriptive table anywhere where that exists. I certainly would consider having the anchor bolt spacing and the vertical reinforcement all line up in the same cell so that when you grout or concrete in the cells with the anchor bolts, we've got a continuous load path through from sill plate down to foundation, down to footing. There are some flood issues related to crawl spaces. We need flood vents in foundation walls in floodplains in order to equalize hydrostatic pressure. FEMA's got prescriptive guidance on how many of those flood vents you need, or at least in terms of the number of area of those total flood vents. And then there are some prescriptive guidance on how they should be spaced, how many you need in each wall, etc. You can't put solid foundation walls in what FEMA calls V zones or high velocity zones, so those foundations have to be open. And the inside of the crawl space has to allow water to drain back out, so you can't really create a basement with a really low floor in a crawl space once you've gotten water in it. So let's look briefly at our load combinations because we're running out of time here. So these loads came from our webinar 3. And we have tension loads in this particular case on both sides of the building. When we have sliding, then we have 2 places for the building to slide. We have the interface between the building and the foundation. So here we have to resist the wind loads at this lateral interface. And we can use the weight of the building to create friction here, so the weight can be used. And then we have shear resistance that includes all the loads, including the water loads, down here at the pile to surface ground interface. These are the combinations that we use. Now remember, the wood frame construction manual is using allowable stress design as the design basis and has already included the weight in some of those calculations. So to me, I've illustrated what I think the most restrictive combination is, and these are from ASCE7's allowable stress design load combinations. Notice how much we don't know about the flood, because our load factor for flooding, even in the allowable design basis, has a multiplier on it of 1.5. Now we've already reduced the wind pressure for ASD. That reduction has already been accounted for. So, but we do have a multiplier in the ASD load combinations for flooding. And as I mentioned, we can use the frictional resistance of the house to resist sliding, and thus the inclusion here of consideration of the weight of the building. In terms of overturning, now we use all the loads. It's the typical way we do overturning. Loads times moment arm gets you a moment. There are several places here you could take the moment. I have decided to take the moment down here at this point of fixity because, again, this is a foundation design discussion, really. So I'm more interested in this discussion in what happens to the whole building. I don't want these piles to break off. I don't want them to pull out of the ground. So I'm using the point of fixity as the distance D here. But you could, if you were looking mostly at the box, at the connection of the building to the top of the foundation, you could fix this building about the point where the cursor is pointing now. The load combination, again, is number 7. I have discounted the weight here because the weight is already considered in the wind loads. So at least in calculating this using the wood frame construction manual, you would not include the weight again. We do have compression loads that come into play. So you have tension load on one side that's being pulled up and being pushed on the other side. I do think our overturning moment needs to be considered, and that compression that happens on the left side of the building needs to be considered in the compression on the pile. A couple of quick slides about cross bracing and various ways to support the building. This way actually is a pretty well thought out way for grade beams. Obviously the soil under the grade beam has been eroded, but the grade beam has at least been constructed such that it will clearly span between the piles and be self-supporting, and so there's enough steel in this grade beam to resist a failure even though the soil has been eroded away from underneath of it. Breakaway walls are required in coastal areas. FEMA's got guidance on breakaway walls and requirements on breakaway walls, and I won't go into a lot of depth here about breakaway walls. Just know that if you're building in a velocity zone and you want to put an enclosure around the piles, those enclosures have to break away. And the breakaway requirement is all fixed to what the load on the wall is. The maximum load is, it says, not to exceed 20 pounds a square foot, but believe me, if you have a flood come along, the design flood will always be a lot higher than wind load, and so walls will always fail from flooding. What we're trying to prevent here is having a contractor with a nail gun in his hand walk around the area where there's a breakaway wall and think that it needs to be nailed like the third floor needs to be nailed. So trying to get people to at least think about the actual construction of these breakaway walls. FEMA's got a technical bulletin on them with a fair amount of prescriptive information. Tells you how many nails to use based on wind speeds and pile spacings. And so if you're in the need for, or you have a design that's including breakaway walls, I'd get my hands on this technical bulletin, which was just redone a few years ago. And with that, let me stop and see if there are some questions.
Thank you, Bill.
Yep.
This was great, and we did have a couple questions come in during the presentation. We can tee up here for you. Talk a little bit from a code enforcement standpoint about FEMA 55 versus design documents like the NDS, which are referenced in the code, and how are those accepted by building departments in these coastal areas?
It varies all over the place, buddy. There are a couple of places, and I think I've heard New York tell me that there are some places in New York that have actually adopted the Coastal Construction Manual as their method of construction and enforce it as part of their code. And then there are others that don't do that, but the manual itself is using ASCE 7, the International Building and Residential Codes, references like the Wood Frame Construction Manual, all as input into the manual, so that the user of the manual basically can follow, create a code-compliant design, or have enough information to follow a prescriptive design that should be easily approved by a building code official on the coast. So it varies quite a bit about what specific code officials or communities are allowing in terms of how much people can use the manual.
Okay. Thanks. As a follow-up to that, then, you showed some examples of cross bracing and knee bracing, grade beams. Are those covered in the FEMA 55 document, or do you need other resources like the NDS to design knee bracing and cross bracing?
They are covered in the Coastal Construction Manual. You should use something like the NDS to actually design a cross brace, particularly a cross brace, if you had piles widely spaced. And you would primarily use something like the NDS for two things. One would be to all the braces are assumed to be tension braces, so when the wind is blowing in one direction or pushing the building in one direction, those braces act in tension. And so the connection, where the bolts are placed between the cross brace and the pile, obviously needs to meet the requirements of where you can drill holes for bolts in members like 2x8s and 2x10s and 2x12s. And what kind of tension those members would take. So that's where it would mostly come into play. Grade beams are almost always concrete. There are some connection details in FEMA 550, that foundations guide I mentioned a long time ago, that provides some connection details between concrete grade beams and wood piles. Knee braces are typically, there's not much engineering to those necessarily. Again, they're tension-only braces. You just want to make sure that you don't put a moment or induce a moment into the pile that you didn't intend to induce, at least one that you couldn't handle. So that's the primary consideration for things like knee braces.
Well, that's great, Bill. Thanks so much for this excellent series and presentation. That's all the time we have for questions at the moment, and I'll remind folks that we'll be following up with additional questions that we weren't able to answer here via email. In fact, the Q&A, the questions and answers from the first two webinars are already posted to our website, and so you can get to our eCourses page and view those, but you'll receive an email about that. So thank you once again for joining us. If you do have an opportunity when you get the follow-up email, please respond to the survey. Your feedback is very important to us, and we hope you've enjoyed this series. We once again express appreciation to Bill Colburn for contributing his expertise in this area. Finally, a reminder that we do have two more topics added to our schedule. November 21st, we'll be presenting another prescriptive residential wood deck construction guide, DCA 6 webinar, and then January 16th, one of our newest publications in partnership with ICC is the Code Conforming Wood Design document, and we'll be presenting that the first of the year. So you can see our website for additional registration information. Again, thank you for joining us, and have a great day.